Hello, in this presentation we will discuss the results published in the paper Solvent Effect on the Regulation of Urea Hydrolysis Reaction by Copper Complexes. I'm Mikael de Castro and the data presented here was obtained during the master's degree. This work was accepted on July 17 this year and published on June 2nd in the Chemistry Journal. Until the last check on July 28, it was the most viewed and downloaded article in the journal. This shows us that the subjective address of interest to the scientific community. Thus, I will start by commenting on the theoretical basis and reports from the literature that justify the development of this work. Allosterism is a type of enzyme mechanism that regulates the catalytic activity of enzymes, in this case, allosteric enzymes. So, by definition, allosteric transition is based on conformational change, or induced fit, of the active site of target protein upon binding of an effector to this protein at a specific site, distinct from the active site. This is a definition put forward by Doclan in 2016. This conformational change is illustrated in the figure on the left, where the three mechanisms that can occur in allosterism are observed. In A, ligand-driven ligand binding, that is the most naturally observed mechanism. And B, ligand-driven disruption protein-protein. The association of a ligand induces conformational change in a protein that abolishes interaction with the appartenant protein. And in C, D is the ligand-driven dynamic coupling. There are many examples of allosteric enzymes in nature. A metal enzyme essential for the functioning of our body is hemoglobin, represented below. The mechanism in hemoglobin is a mixture of mechanism A and B because the substrate itself, which in this case is oxygen, acts as an allosteric activator, changing the conformation of the enzyme and enabling the attachment of more oxygen molecules at the other binding sites. For this reason, the enzymatic allosterism are targets of inspiration on the part of scientists in several areas, such as, for example, the drug development in specific targets in biology field, as well as in the modulation of catalytic activity, as in the synthesis of catalysis in the field of chemistry. More specifically, the mimicry of enzymatic allosterism can provide the ability to make targeted catalysis. In this context, a few research groups around the world have tried to synthesize coordination compounds that have catalytic activity similar to enzymatic allosterism. One of them is the group of research shared mimicry. One of the applications reported by them in this article, which they tried to develop the sensor mechanism that responds to binding of small molecules. So, in this work, they developed a system that mimics the properties of PCR using a rhodium-1 tetranuclear complex which can have its structure open in the presence of chloride or acetate to generate a cavity capable of catalyzing an acyl transfer reaction between pyridyl carbonyl and acetaldehyde. When they graphed the results, what was observed was a sigmoidal pattern. Slow induction followed by rapid exponential amplification, linear growth, and then eventual saturation. The conversion rate becomes maximum at saturation and decays with time, logically the first derivative. This catalytic profile is characteristic of an allosteric behavior. So the weak link approach, better known as WLA, it is a way of building molecular structures which can have their conformation regulated from the association of weak ligands. These ligands are added to the medium so that there is a substitution reaction with ligands coordinated to the metal that have sterically higher coordination points. That is, they facilitate the conformational change through concatenation. These are called hemilabile ligands. The figure on the left will facilitate this explanation. In A, it is observed the traditional WLA approach, where there are ditopic ligands with the same functional groups, which are complex in closed mode with metals, preferably DH, representing by 2. When the groups are superimposed and the addition of anions that can act as a weak ligand, for example chloride or acetate, as we saw earlier, allow the structure to open. If there is a catalytic activity portion, catalysis will begin, whatever it may be. B and C derive from the traditional approach, and B, ligands with distinct functional groups with one of the coordination atoms. In the case of Z, it is more sterically prevented, which allows the formation of species already in open mode. In addition, C, which is a mixture of the previous two, when using single dentate and bidentate ligand in the same proportions, forming a layered complex in closed mode. In open mode, it gives access to two different catalytic structures, A and B. This allows the possibility of forming sequential catalysis, where the product of one catalytic site is the substrate of the other. Looking now at the complexes synthesized by our group in analogy with the literature, generally bimetallic complexes have catalytic activity superior to monometallic analogues. An example is shown in the illustration above, where a cobalt-2 bimetallic complex has catalytic hydrolysis activity 13 times greater than the monomer. Interestingly, the approach he used to build the dimeric structure is the insertion of urea in the second coordination sphere, which acts by means of intermolecular hydrogen bonds with a subsequent molecule of the complex, thus forming a supramolecular structure. This is a very interesting approach in mimicking enzymatic structures. Another alternative in the construction of supramolecular structures is through chloride bridges. These bonds can allow the creation of dimeric to even polymeric structures, as can be seen from the crystalline structure above. They also have sensitivity to the environment, which can be broken down by solvent molecules or even small molecules that can act as a ligand, forming smaller species to monomers. This is an interesting approach. Also was a way of regulating species in equilibrium of the catalyst, intercalating between active and inactive species with the objective of modulating the catalytic profile. Based on what was said, the compounds synthesized in this work were divided into two steps, where the Schiff-based ligands were obtained at 6 reaction steps, starting from the amino acid L-proline. There were altogether 5 ligands, which varied according to the substitution group, which were hydrogen, methoxy, methyl, butyl, and ethoxy. In this way, 5 copper complexes were obtained by reacting the ligands with a copper salt, which varied between chloride and perchlorate. The compounds have been completely characterized by various techniques. After characterization, the synthesized complexes were applied in a model catalysis to evaluate the species in equilibrium observed during the characterization. This reaction was the hydrolysis of urea, where the Berthelot method was used to quantify the ammonia from hydrolysis. Urea hydrolysis catalysis assay took place in Eppendorf, where 50 microliters of a standard solution of the complex in 850 microliters of organic solvent were added. The nanoliquid of the standard urea solution was added, which depended on the condition of water and urea concentration required for catalysis. This reaction mixture was stirred vigorously and the temperature was controlled at 36 Celsius degree, and a 100 microliter rate was taken at the analyzed times, which were 5 seconds, 10, 20, 30, 40, 60, 120, 240, and 480. Ammonia was quantified using the Berthelot method. The samples were analyzed by UV spectroscopy at the wavelength of 654 nanometers. It was necessary to construct a calibration curve with ammonium chloride as a standard for effective quantification. So, initially, the compounds were synthesized and completely characterized. The data obtained were consistent with the proposed structures and can be seen in the support information of the article. The complexes were also characterized. It was observed the data were consistent with the proposed structures, where some of the techniques showed that the complexes exist in equilibrium solution. Therefore, in the next slides, these results will be discussed, which were important for the understanding of how complexes act in catalysis. First, the mass expertometry analysis of the complexes showed that there are both monomeric and dimeric species, as in this example for the complex with electroligand, in which a main peak can be observed due to the mass of 538, as well as a peak above 1000 that was attributed to the binuclear structure on the right associated with a sodium ion. However, as it is a technique carried out at high vacuum, this is not a 100% reliable result, and is therefore not conclusive. In this way, experiments with other techniques were carried out. Conductivity was the first technique performed to investigate the replacement of chloride in the coordination sphere. Since through mass expertometry, it was seen the monomeric complex is consistent with a structure without the chloride. So, in dichloromethane, the complexes were neutral, which was to be expected because it is a non-coordination solvent. However, in acetonitrile, in figure A, it is observed that there is an increase in conductivity with time, independent of the complex, but more pronounced for the complex with methoxy substituent. This increase is enhanced by the addition of water in the medium, as can be seen in figure B. This result indicates that water accelerates the chloride exit from the coordination sphere, possibly forming a monomeric aqua complex, according to the proposed structures. However, when the conductivity is evaluated in methanol and methanol water mixture, what is observed is slow increase in conductivity, which indicates that chloride is being replaced over time. However, the values do not reach the level of charge electrolyte 1 positive. This indicates that in these two systems, there is equilibrium between species that differs for complexes with methoxy and ethoxy substituent, shown on the left, and for methyl and butyl on the right. What is observed is the addition of water affects the complex with alkyl substituents more significantly, possibly because the substituents with oxygen as heteroatom can interact with the bridge chloride, reducing the effect of water in the substitution reaction, which must happen through charge polarization through the coordinated halide. Still, the results are not so conclusive. To improve our proposal, experiments of electronic paramagnetic resonance were carried out, which allows observing the change of ligands and geometry of copper-2 complexes. So what was observed was that in 77 Kelvin dichloromethane, the complexes have a component related to complexes in molecular aggregation, according to the theorized spectrum compared to the experimental one. The same trend was observed when the complexes are placed in acetonitrile and acetonitrile water, proving to be a characteristic of the system itself in solution. In addition, the correlation times for the complexes in the different solvents were obtained, which enabled the calculation of the dynamic rotation radius and consequently the volume of molecular aggregates considering a spherical system. It was observed that there was indeed a reduction in volume when the complexes are in coordination solvent. This indicates that, in fact, the complexes in neutral state are the form of molecular aggregates, which reduce in size in coordination solvents because there is the substitution of chloride forming smaller species, that is, monomeric. This indicates that the formation of supramolecular structures occurs through chloride. So, the results of FTIR were relevant to investigate the geometry of the aggregates. Since analyzing the values of GZ, it was found that for complexes with the ligands L2 and L5, GZ was greater than GX and GY, and the opposite occurred for the other complexes. This indicates that it can be seen by this figure on the left, and which was corroborated by theoretical calculations that the complexes with methoxy and ethoxy substituent have molecular aggregates in axial geometry, where not only the three coordination atoms of the ligand are found in the plane being completed bridged chloride. In contrast, the other complexes have a trigonal bipyramid geometry. In order to verify the relevance for the supposedly bridged chloride, the perchlorate complex analogy with the ligand L2 was synthesized. The results of FTIR in methanol and methanol water show that the perchlorate complex exists as a unique and stable species, whereas the chloride complex has a mixture of compounds with the monomer-dimer equilibrium. In addition, the correlation times showed that the perchlorate complex has a slower rotation in solution than the chloride complex, and this indicates that such complex is dimeric. The mass spectrum of the complex perchlorate and methanol corroborated the result, as it showed a peak in the following structure, where the perchlorate is bridged between the two copper centers. This structure was aligned with the other characterizations. In summary of the results of characterization of complexes and state of equilibrium of species in solution, it was observed that in fact the synthesized copper complexes exist in equilibrium in monomeric and dimeric forms, and then from bridges for chloride, such complexes have the ability to form molecular aggregates that can eventually form multinuclear structures, depending on the extent of these interactions. In addition, with the comparison made by obtaining the perchlorate complex, the fundamental role of chloride is assessing this equilibrium and, who knows, controlling it. And that was observed too. To better illustrate, this figure shows the equilibrium scheme that occurs between species dependent on the environment. On the left side for complexes with oxygen as helioatom, which even in the presence of water, the monomer-dimer equilibrium is maintained. A red complex with alkyl substituents are more sensitive in the presence of water, as was seen in conductivity measurements, causing the equilibrium to be shifted to monomers. So, after that, the complexes were applied in the catalysis. First, two solvent systems were used in acetonitrile water in figure A and methanol water figure B. Clearly, there is a difference in the catalytic profile depending on the type of solvent, where on the left side we see a tendency to decrease, quantify ammonia, and increase with saturation on the right side. The same trend was observed for all complexes, and this indicates that the reaction in acetonitrile is quite fast, occurring even before 5 seconds. In methanol, the reaction is slower, suggesting that it depends on the monomer-dimer equilibrium. For this, to evaluate this dependency, the reaction with the perchlorate complex was carried out, and the same tendency of decrease in acetonitrile and increase in methanol was observed. However, the amount of ammonia produced was lower, as in methanol the reaction was slower, showing that the dimeric structure is also active but slower. It is known that there are significant differences between the action of acetonitrile and methanol in water. Since acetonitrile is an aprotic solvent, and therefore the hydrogen bonds with water are less effective, in fact weaker, compared to those that occur in methanol water. Thus, the role of the solvent was better evaluated by carrying out reactions in 3 more solvents, as can be seen in the figures. The left in DMSO, the right in THF, and the middle in ethanol. This observed exactly what was expected. The reaction is faster in polar aprotic solvents, while in polar aprotic solvents such as methanol and ethanol, the reaction is slower, and it is possible to observe the product's quantification saturation profile during the analyzed times. So, to better explain this behavior, theoretical calculations were performed to verify the energetic effect of the solvent. First, in figure A, we see that the solvent interacts with hydrophobic sites in the complex and the second coordination sphere, generating the first hydration radius, forming a third coordination sphere by pole interactions with the water molecule. What happens that in the system with a strong hydrogen bond, there is a reduction in the energy of the fundamental state by stabilizing the beginning of the reaction of equation. This causes the energy barrier of the substitution reaction to increase, slowing the reaction, exemplified by the energy diagram in the figure B. Then, as the reaction in methanol water was lower, it was possible to analyze the kinetic parameters of rate reaction, and catalytic constant, and in these graphs we can observe the influence of water on the complex that exemplify the two different trends observed. For complex with alkyl substituent, the sigmoidal profile is observed regardless of water concentration. In other words, this indicates that for these complexes, water actually potentiates the action of active species because it precisely acts to favor the balance of monomers, which reaches the saturation level with maximum rate, as observed in an allosteric behavior. For the complex with L2 ligand, increasing the amount of water increases the rate reaction linearly. This is an indication that water is not only acting as a molecule that determines the conformational change of complex, but also as a reactant. So, based on what was already being observed, the other effects on the catalytic activity of the complex were studied. One of them was water activity, which is a measure of the availability of water in the medium to make the reaction. Variation in water activity can change the path of hydrolysis reaction, and the result obtained was that the activity has a similar role for the complexes tested up to approximately 0.6, but after that point, it has greater influence on the complex with L3 ligand, which corroborates the previous results than for the complex with alkyl substituents, a water determines the maximum of the reaction. As in the lowest condition in acetonitrile, water already has an activity of 0.9. The faster catalysis behavior could be explained by the excessive water activity in the system. However, a new catalysis was performed using as little water as possible in acetonitrile with an activity close to 0.4, observing the same behavior regardless of the activity. This reinforced the hypothesis that in fact the solvent, the type of organic solvent that interacts with the water in the medium, plays a fundamental role in the catalytic profile of these complexes. The other fact evaluated was the pH of the medium, where the experiment with the addition of phenol red as I indicated before and after the reaction did not show any change in pH. In fact, the pH of the ammonia-ammonium buffer may be lower in mixture with organic solvents. Then, an in situ FTIR experiment was carried out where the appearance of a broad band in the 3000 cm 1 negative region was observed, which is indicative for the formation of ammonia ions, and after 90 seconds of reaction, insulation of this band was observed, indicating that the species in fact they can be in buffer equilibrium. In this way, new reactions were carried out with phosphate buffer pH 3, 6, and 8 to observe the influence of the reaction rate, and what was observed was that the reaction is catalyzed at both acidic and basic pHs. What was observed in the figure D. However, with a lower rate at relation to the non-buffered reaction. Then, summarizing the published study, 5 new copper-2 complexes were synthesized through proline-derived Schiff-based ligands, which were observed to be complexes that can form monomeric and dimeric structures in solution, even molecular aggregates dependent solvent. And The presence of bridge chloride plays a fundamental role in this structuring. This behavior, evaluated by the Urea hydrolysis reaction, showed that the complexes have catalytic activity that can be regulated in water by the type of associated organic solvent. The hydrogen bonding force between water and this solvent is crucial for stabilizing the system. So, I would like to thank the laboratory to which I belong and where the work was developed, as well as the members of the laboratory. I also thank researchers João Honorato and Otacílio Rangel for the collaboration with crystallography techniques and EPR studies. And I also thank the funders CNPq, CAPES, and FAPESP. Thank you.